Super quick, who am I? I am Dan Golden. I've been at TripleLift for 5 years. I joined when we were 12 people. We're about 200 now. And we're an Adtech company that's doing real-time bidding. And I'll get into exactly what that is. The reason I'm talking here is because I was pretty instrumental in, I would say, writing many of the versions in the past that are currently being fixed by others to correct all the mistakes I've made. And we'll be covering in detail. And my goal with this presentation is really to talk about really the narrative of the different steps our pipeline took through its evolution, because oftentimes you'll see kind of the end result and you won't really understand or appreciate like what were the motivations to get there. You won't really realize like, well, what sort of missteps occurred on the way. So I'm trying to be a bit more transparent with the hope that at least others kind of see the trade-offs we have to think about, see the technology choices we made at different points in time. And obviously at the end, if anyone has any questions, everyone could ask. So it's a pretty simple agenda. I'm going to spend maybe about 5-10 minutes explaining like Adtech, because it really sets the context for the rest of the presentation. Because if you don't understand the challenges like within Adtech of like what does the data look like, how much is the data, the rest of the presentation doesn't really make a ton of sense. So I'm going to spend some time talking about that. I'll talk about the evolution of the various data pipeline versions we've had. It's going to be covering like 5 distinct pieces. Keep in mind, I'm going to make it seem very black and white. It was definitely not the case. There's definitely overlap from one version to another version, because that's really what happens when you're building like big data systems. And then the last bit is to talk a few lessons learned. There will be lessons sprinkled out throughout from each particular version of our pipeline, but I'm going to wrap it up by saying kind of 3, I would say like universal or like holistic lessons that we've picked up just along the way that apply to every single thing, or at least some of the lessons we learned along the way. So pretty simple, talking about like data in Adtech. If you do a simple search on Google for Adtech big data, you get millions of results. There's obviously something there. They generally tend to be synonymous. You can't really consider yourself, I would say, an Adtech company if you're also not working with big data. So the question is like why? There's a very simple example. If you load up the New York Times homepage with this Chrome extension called Ghostery, it'll tell you all the analytics and tracker code that's running. So just by loading up the homepage of the New York Times, you see 39 companies' code being executed on that page that are New York Times. They're really just vendors that are collecting stats, like who is the user, how long did they spend on the page, yada, 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 yada. And it's like, well, why? This, at some level, begs the question of why are all these companies collecting this data? Like, what's so special about it? Simple, very quick, simple answer. Auctions, real-time bidding auctions. And I'll do a very quick overview of exactly what that means kind of here. So super simple, if you're familiar with Adtech, this won't be, you can consider this a refresher. If you're not familiar with Adtech, prepare to have your mind blown. What happens is every time you land on the web page that's running advertising, the browser sends an ad request to an exchange. It doesn't really matter what the names are, ignore them. It basically sends this ad request to a server, and it contains information about you, the user, like what state are you in, what time is it, what browser are you using. An exchange then sends it out to a couple to these companies called DSPs that have like basically code proprietary bidding algorithms that'll say, well, oh, it's Dan, he's looking at the New York Times using this browser. How about we serve him an ad for a Toyota Camry? And then they decide how much is an impression to me worth. They submit it upstream back to the exchange, and the exchange runs this second price auction to determine who is the winner of this auction in order to then serve an ad back to the browser to have it rendered, and the user hopefully sees the ad, clicks it, engages, whatever the case may be. So this is happening. If you really go to the website and you see the amount of ads they have, one of these is happening for every single ad. So there's a ton of data really being collected throughout the process, right? Both for the ad requests being sent out, as well as the bidding behavior, as well as all the data people are collecting around engagements. So there's like just a huge, I would say, like pool of data being collected by like every company across the industry. And something that's, I would say, even like super interesting is all this literally does happen faster than the blink of an eye. Like on average, it's about like 200 milliseconds from the very beginning, from the time the request is made to an exchange back to when it's rendered. So there's obviously a strong need to do things like at scale very quickly. So that's a very quick overview of the way real-time bidding works. and sets up the foundation. In particular, talking about the data side of the business, it's useful to think about what data is actually collected at each step, like in a pipeline, or like is being generated at each step of this auction. So, like very simple, in the case of an ad request, it's before any buyer has seen what the information or has really done any evaluation. So at this point, all you really know is really what the user or the browser sends over. So you have IP address, which people use to determine the geolocation. You have the user agent, which is used to determine like the browser, the OS device. You have a few more information, a bit more information around like user IDs. If you've seen them before, you may be able to say, oh, they like have seen these ads. So there's generally information about that particular ad request. The next step is the bid request gets sent to these DSPs, and they're generally similar, but there is some subtleties where different companies have different protocols. There's slight information that's modified depending who you're talking to. Generally, you want to collect this information just because you want to really dig in to identify some issues. So just one of those things that just adds more and more volume. Lastly, once you get the bid responses back, what do you know? You collect information about like the brand, the price. You collect information about the ad itself. Is it an ad for, going back to our example, is it an ad for Toyota? Is it an ad for Samsung? You're really just getting information about the brand, how much they're willing to pay, and then once it's, once the exchange runs this auction determines the winner, like it's not always going to be the highest price, because if the particular website says, hey, I don't want any alcohol ads on my website, if a buyer wants to serve an ad for Budweiser, it's going to get rejected and it'll go to the next highest. So there's a variety of business rules that this exchange applies in order to then send a response back to the browser. And then lastly, as a bonus, you also start collecting engagement metrics, which can only happen in the browser. Like, did the user click? Was it in view? If it's a video, how much of the video did they watch? So all this information is being collected really for every single, or nearly every single event that the industry sees. So this is a bit of a stretch, but it helps me think of like how to think about the problem. If people aren't familiar with the Drake equation, it was this idea of how do we estimate the number of alien civilizations that could communicate with us? And you look at the equation, and it's really just a factor of multiply like 10 different numbers together. Like, what is the rate of universes being created? How long are they active for? Blah, 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 blah. But the general idea, like the parallel to me is, it's a ton of different like factors that you then multiply together to come up with like some sort of number, and it's really this idea of just blowing up sort of your, I would say, cardinality and dimension space. So these numbers I'm going to share are specific to TripleLift, and you can consider us being, I would say, like a small to mid-sized Adtech company. So companies like Google, Facebook, they're in advertising, their scales are like order of magnitude, probably multiples of magnitude bigger than what we do, but also we're not like the smallest company. So like think of it as an example of what roughly a 200-person Adtech company sort of experiences. So high cardinality, what does that mean? If we go back to the previous kind of slide when we were discussing the data pieces being collected, you see that there's browser, you see that there's OS, you see that there's region, you see the buyer. So all these, we have roughly 50 of these, I would say, like unique dimensions for a particular, for a single ad request. So, and you can imagine if you're doing data analysis, that's a lot of data that you have to like slice and analyze and collect over. You couple that with this idea that there's a lot of volume. We're doing 4 billion ad requests every day. Right, so you take the 4 billion ad requests with these 50 dimensions, and some of the dimensions themselves are high cardinality, right? There's 50 states. If you're international, there's a lot more regions. If you're looking at browsers, depending how specific you want to get, you have like 15 browsers. If you're looking at number of campaigns, number of brands, there are like hundreds of thousands of brands. So each of these combined with the fact that there's 4 billion of these happening every day, like seriously adds up. On top of that, you take a look at Adtech, and fundamentally, it's an extremely low value. Like each of these individual ad requests is worth fractions of a penny. So, and this right here isn't, we don't always win an auction. So what really happens is, oftentimes you get an ad request, you submit a bid. If you don't win, you're still paying for the processing, you're still paying for the storage, you're still paying for all of these things you've had to do to that individual event. And if you do win, it's really worth fractions of a penny. So the ultimate idea is, how do you do these things like when we're thinking about a data pipeline, it's how do we still make it successful or accessible to our users while at the same time being cost effective, at the same time being able to like just handle the scale. So I'll dig into like our evolution of the thought process and kind of how we've approached it and the technologies we've used. So this is some numbers. I'm not going to go read them, but if you're familiar with like the various bits of technology here, like I think some of the numbers will stand out. Probably the most interesting one I mentioned is the 4 billion ad requests a day, but that really means we're doing 140 billion bid requests because we get an ad request and then we fan it out to a bunch of different companies, and that sort of multiplies the effect. We're collecting, important part is we're collecting about 300,000 events a second. Like some of the events we sample just because the load's too high, others we collect every single one. So I'm sure this is going to be recorded so you can review the numbers after. I don't want to read every single number, but it's just supposed to frame the size of the problem here. It's pretty big. So now talking about the actual evolution of the pipeline, and I'll dive in, or before I dive in, I kind of want to explain how we think about a data pipeline. And this is the framework we'll use to really look at our evolution. This is pretty similar to like this ETL analogy, but in the case of like at least maybe an Adtech version, I view it as this idea of there's some events being generated. And right now there's sample technologies that I consider to be within each group. So there's Kafka for storing the events. There's the processing, which is you realize we're getting 4 billion of these events a day. Like we need to do something in order to transform them. So the T and ETL in order to make them and then store them in order to then make them accessible for our users. So, and I'm gonna each of the following versions of the pipeline, we're gonna kind of leverage this idea of the event collection, the processing, the storage, and then the access to think of how our system evolved. So V0, it's purposely 0 because it doesn't really deserve a real version. And it's got implementation highlights and quotes because I would say these aren't really highlights. But the key idea here is when we started, so think of this as 5 years ago, and I'll give a timeline as well at the end just to put things in perspective. But like this is as simple of a pipeline as you can get. We didn't want to collect every one of these events we've seen. It was too expensive. What we do is in the browser, we just have like a little function that says, hey, if math.random is less than 0.1, send an event off. So this is basically saying sample events 1 out of 10. We sent them to a little node application on the back end. That node application would do its aggregation in memory. It would write these aggregations to MySQL every few minutes. And then we'd have another job that would run daily that would take these sampled kind of mini ags and roll them up to a daily level. So dead simple. Each of these 4 steps maps exactly to this idea, like to this kind of framework we discussed. And that's that. So, and this is the framework I'll kind of take thinking through all this. So why did we do this? It was extremely simple. It leveraged all the existing technology we had. It was not a lot of work. And it really gave us what we needed to do at that time. Like at this point, we're a team of 12 people. Like we're not going to be investing in all this like big data infrastructure just because there's just so much overhead, both in like setting it up, but both in the cost of running it. So next, like what challenges do we run into? It's pretty obvious. When we had any issues, we were investigating off of sample data. So imagine trying to do any analysis where you miss 90% of your events, 99% of your events. So that's kind of the challenge we run into. We had a ton of event loss because if there was any hiccup in MySQL, like that insert failed, and we weren't able to collect that data. And also non-scalable, like this entire thing was relying on like one SQL cluster, one node application. We tried spinning it up, more up, it fundamentally just didn't really work as we grew larger. At the same time, like one could get pretty far with a very simple system. Like I know there's a lot of, like right now, especially if you look at like just the amount of tools out there, there's a huge amount. But like the reality is you could get pretty far if you're willing to make some compromises. And it's and only when you really realize you have a problem do you have to think about or taking it to the next level. And there's a little example of an error message we would receive in 2015 when like an insert failed. Right, you would get these emailed to you, and usually they come in batches because it's not like you'd have one failure. You'd probably have like maybe a couple of hundred within the span of a few minutes. So we get this giant email. Someone would have to copy this query, paste it into my SQL client, run it, and like that would fix our data pipeline. So this is I would say how simple things were back in the day. So next version, and this is really this idea of moving away from really the sample idea and starting to collect every single data event and really building, I would say, the start of a modern data infrastructure. So what do we do here? One, capturing every single event. We're starting to use Kafka, which is really, I would say, like the industry standard for collecting like log level data. It's either Kafka or if you're on the cloud, like AWS use Kinesis, but generally I don't think anyone uses like at least in Adtech, anything else, because Kafka just has the scale, the redundancy, the distribution to like make things work. We also started using Redshift with a few hacks in between, and I don't necessarily want to, not sure I have time to dig into each one, but if you go to office hours, I could definitely share it. But generally, we have the data going in Kafka. We use this application called Secor, which was open sourced by Pinterest, and all it does is it reads from Kafka in a variety of different protocols, so either JSON or protobuf or like Thrift. In our case, we use protobuf. Takes that data from Kafka, converts it to another set of output format, so we use Parquet, uploads it to S3, and then it takes that data that used to be in Kafka, uploads it to S3, and then you can do whatever you want with it from S3. What we did in this version is we hacked the hell out of Secor, so after it uploaded to S3, it would also publish a message to Rabbit. And then we had a separate process that would say, hey, the ad request data has been uploaded, or the click data has been uploaded, read it from this S3 location, load it into Redshift, and then we had a whole separate process that would take the data, this log level data from Redshift, and then use it to run ag jobs in order to generate ag tables that were in Redshift once again. So we use here Redshift as both the store for our log level events, as well as the store for our ag tables, as well as the actual like processing engine. So in this case, like Redshift sort of became the bread of what we did. We still, for whatever reason, we'll talk about it later, but we built like a home-built scheduler system. I do not recommend it. You should definitely use something that's already out there. But yeah, so like basically we did introduce a few technologies here, and this is really the start of decoupling the various steps of a data pipeline and really making something that is much more modern, much more in tune with what people, I would say, normally think of as like a big data or big data pipeline. But at the same time, you also see the complexity here. In the past, it was very linear, right? It was like 4 boxes, data from one goes to the next, go to the next. Here, you're already starting to see some branching. You're already starting to see systems being decoupled. And like that's in general, as you get larger and as you build like a real life system, you start to decouple systems. It makes it easier to develop. It makes it easier to test. It lets you, I would say, introduce fault tolerance into your system. Like in our case, if any of the ag jobs failed or the log, like the log loads failed, because we still had the data on S3 because of Secor, like we didn't really have to worry about it. Like our pipeline became then suddenly delayed by a few hours or maybe a few minutes instead of actually having to like actually lose data, like which is like the big no-no in the industry. Yeah, so like pretty simple. Like why do we do this? Really, we needed to move towards log level events. We just couldn't really work with sampling anymore. We obviously wanted the resiliency and scalability. Like what challenges did we run into? A big one was when we moved to Redshift, we realized that every single piece or every time we needed to do an ag, we had to do it through SQL. And SQL gets you pretty far, but we couldn't do anything that was statistical in nature. Or we found ourselves working over backwards to do like queries that use like nested queries, to use window queries, to do things that would have been much simpler through code. But because we were on Redshift, we really had to use SQL for that. The next two are pretty interesting. Like one is what ended up happening is as our users, both internal and external, saying, hey, we need this dimension exposed. We need, let's say, we need a table that has domain. We need a table that has browser. We need a table that has region. What ends up happening is you end up having like these aggregate tables per specific use case. So by the end of it, we had maybe about like 3 dozen tables designed for different use cases the customers wanted. And while it was nice from the standpoint of performance, it got pretty annoying. Like fundamentally, we were thinking for something like, is there one way for us to just put everything in one giant table that's actually cheap and performant that could give us that could still give everyone like the ability to like slice dice the way they wanted to. Yeah, job scheduling always a problem. Just like an example of something we ran into as an example of like a job scheduling issue is once we had too much data, what we ended up doing is we started having like daily jobs, and they're like, oh crap, we have too much data. Let's switch them to hourly. Oh, what happens if 1 hour fails? Oh, rerun that hour, but that hour suddenly is linked to the day, and there's this other ag that's based on this other ag, and we had to do all this, I would say, like home built. So it was not a fun problem. I would probably say we spent more time than we should have on just doing the simple stuff of like wiring jobs together. Yeah, and lastly, what we realized, like why we ended up over time moving away from it is Redshift just got prohibitively expensive. We initially stored like maybe 2 weeks worth of log level data, then a week, then 3 days, then 2 days, just because we couldn't store all that while still being kind of price conscious. Yeah, and then another big lesson, we forked Secor way back when. We never touched it since, so we really didn't get to take advantage of any of the new kind of solutions or new performance improvements it came with. right? And because we were like, let's not avoid breaking anything, we kind of kept it the way it is. So I would suggest not forking open source code, or if you fork, contributing back to the main repository. So a continuation of like a newer version. This is where we ripped out Redshift for the processing and replaced the processing part with Spark, which is really a way to write distributed, I would say, like computational code. It's I don't know if everyone's familiar with it, but generally you're writing code in either like Scala or Python. They also have like R code, and it spins it up through a cluster, and it really works on this idea of like resilient data frames, where if any one node goes down, it will replicate it to another node and do really a series of map reduce operations to kind of do the actual data processing. The nice thing is it took SQL, so it's actually very easy for us to port our code from Redshift to Spark, because Spark has the ability to write SQL. And then we also replaced not all of them, but some of our Redshift, a bulk of our Redshift ags with this product called Druid. And Druid is this really large-scale analytics data store. It was created by a company called MetaMarkets, which has since been acquired by Snap. But what it's designed for is very similar to the way I think about it is it's not based on SQL at all. It's really designed around optimizing one single table. But the way it works is it stores it in backs up on S3, it stores in memory through columnar format, but its key advantage is it's designed for more of these interactive analytics. So it's not necessarily designed to give you perfect results, but it's designed to give you like 99th percentile accurate results with, but able to do it much quicker. So it's like, do you want accuracy? Then use Redshift. Do you want something that's just quick and easy to like slice and dice? Use Druid. And we actually ended up moving maybe a dozen of our sort of Redshift acts to this product called Druid. And we really had one giant file. So when I spoke about we had like 50 dimensions, we really just loaded a file in here, like a CSV file that had 50 columns for dimensions, 30 columns for metrics, and let Druid kind of handle all the indexing, all the optimization. And the UIs around it are actually pretty cool. There's a company called Imply that creates like a really nice tool to like slice and dice data. There's a company called, or an open source product called Superset that also lets you really drag and drop dimensions, immediately see what it would look like. If you've ever used Looker, this is really like Looker that's like without having to hit the run button, it like immediately updates like as you play around with the tool. So it's incredibly powerful. Yeah, so like following the same sort of version before. Really, what was the problem? Redshift really just became expensive. It just didn't become like cost effective for us to use it anymore, and we wanted to move away from SQL. What challenges did we run into? We've gotten to the point here where migrating data from like one system to another system is not very straightforward. I think anyone here who's worked on like regular code, like what do you do? Oh, you deploy a new version of your code, everything's great. Oh, it sucks, roll it back, deploy another version. You can't really do that with data. If you have 3 years worth of data and you're like, well, let's load into another database, like that's gonna cause either a lot of time or a lot of money, probably both. So like that's a big challenge we ran into moving data from like one system to another. We really ended up taking a compromised position by saying, hey, let's not load every dimension we ever had. Let's just sort of zero out or null some of these dimensions just to get older data in there and have the top level metrics make sense, but not necessarily have any of the low level, like the ability to like slice dice. The other thing is, we were at this point the team's pretty small. We were like 2 or 3 engineers, and it's like now on top of like the Java system, on top of Kafka, on top of like knowing the Redshift world, time to learn Druid, time to learn Spark. So like these are all like new technologies that our team had to learn, and you go pretty far, kind of reading documentation, trying things out, but it's just something of concern, right? Like over time, you end up introducing more and more complexity to your stack, both from a knowledge standpoint, but also from a maintenance standpoint. And yeah, and lastly, this is something that I really like I found from this step to be, I would say like the major lessons for me is, one, S3 is extremely versatile. Being able to like just dump data onto S3 and then have whatever system you want process it, whether it's Spark, whether it's loading it from like S3 into Redshift, like it's just this very nice cheap data store that gives you this optionality to build whatever tool on top you want. The speaker before talked about Snowflake, like you could load data from S3 into Snowflake, so now you have a completely new sort of database based on that same log level data. So I recommend like just using S3, storing as much data as you can. It's generally much cheaper than anything else. It's cheaper to even like store multiple versions of the same data in different like formats just to improve your query time, computation time. And then lastly, like I'm not trying to be like hyperbolic here. Like SQL really is wonderful. It existed since like the 60s, 70s, and like we still use it. And like you just copy data. Like we really, literally to migrate from Redshift jobs to like Spark, we just copy and pasted the queries, changed the table names, and it works perfectly fine. Like it's just incredibly powerful being able to do that. So almost at the end. This is second to last one, and the idea here is we introduced the Lambda architecture into our system. If people aren't familiar with the Lambda architecture, it's this idea of have a real-time system and a batch system that run side by side and write to the same desired data store. So the idea being you could have a real-time system that's running minutes behind, seconds behind. It doesn't do the perfect job in terms of accuracy, but it gets you directionally correct data much quicker. And then 3 hours later, 4 hours later, when the batch system catches up, you sort of overwrite that data with the more accurate data that was generated by the batch system. And Druid, which is which we've been using for this, supports both. So Druid let us load both data from these like Parquet, like CSV large batch files, but it also let us read directly from Kafka. So if you can see here, we kept the batch system as we had from before. We introduced this other we introduced VoltDB, which let us read data from Kafka. Volt would do these joins in memory. It would publish them to another Kafka topic, and then Druid would read from that Kafka topic, put it into the same data store, and then none of our API tools or like BI tools really had to change, which was actually pretty incredible, being able to say, hey, suddenly we introduced technology. We didn't really have to change like the interfaces at all. We just had to make a configuration change in Druid, and now we have data that's like delayed maybe like a minute, like even less in some cases. So just being able to like do that was pretty powerful. Yeah, so we introduced VoltDB here, which is, this is my sort of like blurb on like how I think about it. I'm sure it's much more complicated than that, but it's able to run extremely high performant loads. It's meant to be like a transactional like database, so think like MySQL, but it's supposed to be much more performant because you're defining all the logic that's going to run on it ahead of time. So it's compiling it, and the way it stores data is going to be optimized for the queries you're going to be running. An example, like a concrete example in our world is we have an event called an auction with an auction ID. We have a click later on with also an event auction ID, and we really just want to join them by auction ID in order to kind of determine, did this auction have a click, yes or no? So the way VoltDB worked is you would tell it ahead of time, fundamentally, hey, we're going to be joining on auction ID. When it loads the data, it makes sure it shards it. It basically says all the auction IDs ending like, or the same auction ID, depending no matter what the event type, will end up being on the same partition. And then when you run the actual queries, it does the queries at a partition level. So it runs, it doesn't have to shuffle data between partitions, it doesn't have to shuffle data between nodes. It really does everything kind of in these like vertical buckets. So that's how we were getting like that high-speed performance there. Once again, like, why do we do this? We really just wanted to maybe too bit of a strong word, but we wanted faster data because waiting 3 hours just took a very long time. Especially when we did deploys, we wanted to see how things worked or debug newer campaigns, or like every time we launched a new publisher, we really wanted to get faster information. Yeah, and we did a little proof of concept and ended up working well, so we stuck with it. What chances did we run into? Yet another technology as we go down the road of big data. And a whole other thing, we spent a lot of time trying to go through like versioning, like upgrading versions. We upgraded versions from Kafka like 0.8 to 0.10. Before we did this, but then VoltDB didn't have the appropriate connectors. Druid didn't have the appropriate connectors. There were some subtleties in the like release notes, which is performance is going to suck when you upgrade, and sure enough, it sucked. But we only found out in production because our stand environment didn't have the data volumes. So, long story short, like this has caused more trouble than it was worth. And then. Yeah, and separately, what do we do here? Just tuning production systems is tough. Like you do all these tests on sand on your like dummy data sets, you deploy to production, and things are very different. So we do all sorts of problems. And lastly, Lambda architecture, very elegant. Just this idea of having batch and real time and combining them, it's pretty awesome. So then this is the current version. So I call it less is more. I know I don't have a ton of time here, but what we really did is we replaced VoltDB because it was expensive. It was yet another language. We realized we didn't really need the full like sub-second minute delay with Spark mini batches. We tried streaming, we ran into some problems, and we decided that Spark batching was okay. At least run it every 10 minutes instead of every like waiting 3 hours. So, and then everything else really stayed the same. So scaling issues with VoltDB, we had to move back. I'll talk a little bit about it later, but it's hard to think about scale without thinking about paying. Almost always, you could, if you want performance, you could get performance, you just have to pay a lot more. So when you're saying, oh, we couldn't do this, we ran into scale issues, you're more likely than not you ran into like money issues, you just didn't want to pay for it. Yeah, so part of it is we did end up reducing time. Instead of like having results within a minute, we suddenly had to wait like 30 minutes. Lastly, we did spend a ton of time using, one thing I didn't mention was we finally introduced Airflow, like a real scheduling system, instead of resorting to our own like home-built system. And then other thing we realized as we've gotten bigger is just all things to all people is not a scalable strategy. You give a user data and they suddenly basically say, hey, I deserve this data for the rest of my life, which makes it very hard for you as like a data engineer or data engineering team to sort of rip data away from them. So, and that's sort of the challenge we have now. We're trying to remove data. We're trying to kind of actually optimize for performance, and we just can't because so many people are hooked on the data. Running out of time. This is a very quick slide just to give some perspective. This was 5 versions over, I would say, like 5 years. Each one's roughly maybe a year and a half lasted. This is a simplification because there's a ton of overlap between one system for another. Even now, we still have some aggregate data in Redshift because it just hasn't been a priority to move it away. And then 3 key lessons learned. One, this is a squirrel eating a giant nut. The idea is don't bite off more than you can chew. And the lesson here is if there is a ton of tech, just by being at this conference, like you realize that there's Snowflake, there's DBT from the previous conversation, there's like Kafka, Spark streaming, like Kafka streaming. And as much as you as an engineer want to try every single one, you really have to keep in mind that as your team, like you ideally want to grow your team, at the same time you grow the complexity of your stack. Like one engineer cannot manage a Druid cluster, a Kafka cluster, like a Volt cluster. It just doesn't make any sense. So you really have to think about the technology you use along with the resources and the people you have. Part of it is using open source is great. Using vendors is great. Like they offload some of it. Like VoltDB helped us do some of the work. Using like Snowflake, they'll do some of that work too, but that's the price you're paying, and that's something to keep in mind. I'm not going to play these videos, or I guess I don't have permission anyway. This is me not publicly sharing them, but this was me recording the documentation, scrolling through the documentation for Kafka, and then the other one scrolling through the documentation for Druid. And it's a 30-second clip each, and it's basically insane like how much you can configure in Kafka. And you get up and running, everything works great, you get a high enough volume, and then you realize, holy crap, all the configurations we did 3 years ago no longer make any sense, and no one has the knowledge to do it. And we've run into this again and again and again, where it's like just doing the DevOps and like the configuration for like big data system is just extraordinarily difficult. And part of it is because someone on the DevOps team may not have familiarity with Druid. Someone on the data team may not have familiarity with Druid. And it's this sort of like no man's land of being like, how do we optimize and how do we tweak and tune our systems? And then lastly, yeah, I hinted at it earlier, but unless you're the size of Facebook or Google at like a real huge company, like in our case, we really weren't limited by technology. We were really limited by like money. Like we just can't afford to do all the systems we want. And that's why we have to come up with these like, I would say like simplifications. And I suspect companies that are like similar size, like your challenge isn't going to be technology, it's going to be like making it cost efficient. And that's it. So thank you. Questions?
Thanks for the talk. I just have a question about the design choice in choosing Spark as your batch processing execution engine as opposed to something like Redshift Spectrum. Have you looked into that? And can you speak about that?
Yeah, no, it's a great question. The simple answer is when we moved to Spark, Redshift Spectrum didn't exist. So like that's the very simple answer, and like at some level we've committed to Spark already. I still think it was the right choice because our data science team is also using Spark right now. So it's sort of nice that there's this shared like experience and shared knowledge of the Spark system that both teams could benefit from. It does also decouple you from Amazon somewhat. Like we do use Athena, for example, in some cases. Like for some of the queries where we want to query our logs directly without really investigating the true data pipeline, we will like after we upload the data to S3 from using Secor, we have another job in Airflow that will index it and load it to Athena. And then and then for Athena, we really just have like a few simple jobs, a few simple like queries to go off of that instead of having to go through like a whole separate Spark system. So I think it's really understanding your use case And honestly, we haven't explored too much because we were already in Spark land.